Hello, everyone. Waiting for a couple more viewers. You ready for this lesson today? It's going to be a doozy. This is one of the ones where it's like, oh, okay. AP Physics C, E, and M is a little bit tougher than AP Physics C Mechanics. And this is one of the lessons where that begins to become apparent. One of the things about electricity and magnetism is it's like mechanics, you use calculus, but in electricity and magnetism, you really use calculus. Salutations! I hope your day is mediocre as always. I have such long eyebrow hairs, and sometimes I'll just be like that, and I'll just like rip out like 5 eyebrow hairs, and then I'm just like, and there's always more. Okay, let's go ahead and get started. Today, what we are going to talk about is the electric field due to continuum charge distributions. Okay. Electric field due to continuum charge distributions. Hey, what's up? So when I say a continuum charge distribution, so we learned how to calculate the electric field at some point P as the sum of the individual electric fields due to the individual charges. Okay. So this was for discrete. Okay. But if we have a continuum charge distribution, the electric field at the point P becomes an integral. Okay, so when you go from discrete to continuous, okay, your sum becomes an integral, and you integrate dE. So remember, D means infinitesimal, all the infinitesimal electric fields due to all the charges, okay? So what is dE? Well, dE, it's a vector, okay? And it's equal to K times dQ over R squared times a direction vector, which I'll just call dV hat, okay? So what this says is this is an infinitesimal amount of electric field. Okay, and we can see that this infinitesimal amount of electric field is caused by an infinitesimal amount of charge. Okay? And then what this says is basically to get the total amount, the total electric fields to get the total electric field, add up all the infinitesimal electric fields. Okay? So just like if we're going to build a human, we build a human out of all the atoms. Okay? You're kind of taking the total amount of electric field and you're thinking about it as being made up of all these little itty-bitty electric fields that are created by little itty-bitty amounts of charge. Okay? So this is how that works. So in particular, one of the things that we will often have is we might have situations where we are more interested, actually almost all the time, we'll more be interested in the magnitude of dE. Okay? And so we know that this is a unit vector, so the magnitude of it is going to be just k dq over r squared. Okay? And sometimes we might want the x component of the infinitesimal electric field, which is just going to be the magnitude times cosine of theta. Okay, so that's going to be k dq over r squared times cosine of theta. Sometimes we might want the y component of the infinitesimal electric field, which is just going to be the magnitude of dE times sine of theta. So that would be k dq over r squared sine of theta. So a lot of these expressions are going to pop up as we do examples, okay? Now here's the good thing. There are relatively few examples you can do without a computer. Okay, so basically this type of problem gets really complicated, or not, I shouldn't say really complicated, but it gets really difficult to solve with the methods of calculus or with the standard methods of calculus. So, we're going to be calculating electric fields as an integral. And in order for us to arrive at a final answer, we have to be able to do that integral. Okay? And there are very few situations where you can actually write down a nice formula for the integral. Okay? So what happens in the laboratory is, and it's never going to happen in the laboratory, so what would happen is you would approximate this integral using a computer. Okay? So now because the AP Physics C exam is a pen and paper test, they are only going to ask you about the examples where you are able to do this integral. Okay? And there's literally 3 or 4 examples where you can actually do the integral. So you just have to master 3 or 4 scenarios that we're going to go over today and next week. Okay? So basically today what we're going to be talking about is the first example. So we're just going to do examples. And we're going to do a line of charge. Okay. With a constant linear charge density with a constant linear charge density which we will call lambda. So let's suppose that we have at the origin here, here's the origin. We want to calculate what is the electric field at the origin. Okay. And this line of charge, it starts, so here's the x-axis, right? It starts at x equals a, and it goes on to infinity. Okay? So it's an infinite line of charge. So what do I mean by lambda? Well, lambda is so when I say linear charge density, it's just the same thing as linear mass density. So linear mass density was dm dx. Linear charge density is dq dx. And so this is equal to lambda. And in this case, it's a constant. It doesn't have to be a constant. You could have the linear charge density depend on location within this line of charge. Okay. All right. Now, if we think about this, what we want to do is we want to look at a tiny piece of this object. Okay, so it's a line of charge, but that line of charge is made up out of infinitesimal pieces. Okay, so let's consider this infinitesimal piece at coordinate x. So this is dq. Okay, this little piece right here is going to create a little tiny electric field right here. Now we're going to assume that this is a positive charge. So a positive charge right here creates an electric field that goes away from it. So it's going to create a little tiny electric field that goes in that direction. Okay? So that is the little tiny amount of electric field that is created by this little tiny amount of charge. Okay? So because this little tiny charge is at location x, how far is it away from the origin? Well, it is a distance x away from the origin, because that's what x means, right? If you're at coordinate x equals 5 meters, then you're 5 meters away from the origin, all right? So that means that the distance, this distance here, from the little piece of charge to where we want to calculate the electric field, that's called r, and that distance is equal to x. Okay? Furthermore, we can see that dE points in the negative I hat direction. Okay? dE points in the negative I hat direction, just because that's to the left. Okay? And another thing we want to point out is that dq dx equals lambda, we can multiply both sides by dx, and we get that dq equals lambda dx. All right. So let's go ahead and write dE. I know that dE is k dq over r squared times the direction vector. Okay? So I know that dE points in the negative I direction. So my direction vector is negative I. Okay? I know that dq is lambda dx. Okay? And I know that the distance of this little piece dq from the origin is x. So that means that r squared is actually x squared. Okay? So if we look at what is a different piece of dq, so this might be dq1 at position x1. This might be dq2 at position x2. So another infinitesimal piece of charge is still going to create a little electric field that points to the left. So the only thing that's changing from one infinitesimal piece of charge to another infinitesimal piece of charge, the only thing that changes is the x coordinate. Okay? So k, lambda is a constant, negative I is a constant. So all of this is a constant except for dx and x squared. Okay? So I'm just going to make that explicit by factoring k, lambda, I hat, all that is a constant, times dx over x squared. So now, how do I get the total electric field at the origin? Well, that is going to be the integral of all the infinitesimal electric fields. So the sum, integral is basically a sum of infinitesimal things. Okay? So I'm going to sum up all of these infinitesimal electric fields. So I'm going to sum up minus k lambda I hat times dx over x squared. Now I can see that my integration variable is dx. So anything that doesn't depend on x can be factored out. So all of this stuff can be factored out. And furthermore, x is labeling where the infinitesimal piece of charge is. And I can see that the nearest infinitesimal piece of charge is at x equals a. And the farthest infinitesimal piece of charge is at x equals infinity. So this is going to go, this integral is going to have limits from a to infinity. Okay? So I'm going to factor that out. So I have minus k lambda I hat times the integral from a to infinity of dx over x squared. Okay? So what I would expect you to be able to do is to get to this step on your own. Okay? Because this step is sort of, all the physics is done at this point. Okay? The rest is just the mathematics of doing this integral. Okay? And I don't really care if you know how to do that integral or not, because you can just plug it into a calculator or plug it into Wolfram Alpha. So I'm not really going to fixate on that part too much. All right? So we're basically done at this point. But I am going to show how to do the integral. But if you don't know how to do the integral, it's okay. All right? So do not panic, because you can always just plug this directly into, Wolfram Alpha. Okay, so the integral of dx over x squared is going to be negative 1 over x. Okay? That's the integral of 1 over x squared, is negative 1 over x. And I'm evaluating that from infinity to a. So notice how when I plug in infinity, I get 1 over infinity, which is 0. And when I plug in a, I get 1 over a. So I do 1 over infinity, negative 1 over infinity, minus negative 1 over a. And so the result of the integral, so basically this integral is going to be equal to 1 over a. Okay? So that means that my answer is minus k lambda over a times I hat. So that's my answer. All right? And this answer makes sense. It means that the further the infinite line is away from the origin, the less electric field we have at the origin, and it means the more charge density we have, the more electric field we have at the origin. So that all makes sense. Okay? All right. So now, let's consider, let's do another example. All right. And so this is going to be a more challenging example. What if we have an electric field that, so here we have a point P. So here's the point P. And it is at okay. It is at coordinate 0, comma, y. Okay, so here's the origin right here. So it's directly above the origin, and this distance is y. Okay, and then we have a line of charge that extends from x equals a to x equals b. Okay, and it has a constant linear charge density. Okay. And so what we want to know is, what is the x component of the electric field at P? All right. So here's the first thing we want to do. All right. We want to just take our system, our line of charge, and we want to just look at a piece of it, an infinitesimal piece of it with charge dq. And this infinitesimal piece is at location x, meaning that this distance right here, the distance from the origin to that infinitesimal piece of charge, is x. Okay? So we got to figure out, how far is this? How far is this from, how far is this infinitesimal piece of charge from the point P? And to do that, we would just use the Pythagorean theorem. So I can see that r is going to be equal to the square root of x squared plus y squared. So that's how far away it is. Okay? This little itty-bitty piece of charge is going to create an electric field that points directly away from it. So if we're at point P and we go directly away from that piece, that little piece of charge creates an electric field that goes in that direction. Okay? So this is my dE. All right? So I'm going to draw dE down here a little bit bigger. So here's my dE. And I want the x component of the electric field. Okay, so here's DE. Here's the y component of DE, and here is the x component of DE. All right? And let's suppose that this angle is theta. So one of the things that is fairly obvious is that DE, the x component of DE is going to point in the negative direction. So I have DEX is equal to, it points in the negative direction, times this magnitude, which is DE, times the sine of theta. Okay? Now here's the interesting thing. Just by the geometry of this situation, this angle right here is theta, right? Now, by the geometry of that situation, these are, this is a straight line and this is a straight line. So this also has to be theta, okay? So sine of theta is going to be opposite, which is x, over a hypotenuse, which is square root of x squared plus y squared. So my dE sub x, x component of the infinitesimal electric field, is minus dE times x over square root of x squared plus y squared. Okay? So now I'll just plug in for dE. So dE here is the magnitude of the infinitesimal electric field, and as I taught you, that is k dq over r squared. Like that. Okay. I know that r is square root of x squared plus y squared. So that means that r squared is just x squared plus y squared. And then I know that dq is lambda dx, just like before. So my dE, the x component of the infinitesimal electric field, is minus k times lambda dx times x over x squared plus y squared. So here's the sine theta term. Like that. Okay. Boom. So now, if I want to know what is the electric field at point, the x component of the electric field at point P, that's going to be the integral of all the infinitesimal x electric fields. So I'm going to take this and I'm going to plug it into here. So I have the integral of minus k lambda dx times x. And one of the things I notice here is that this is, when I multiply these two together, I get x squared plus y squared to the 3/2. Okay? So minus k lambda is a constant. And this integral is over x. So the charge distribution goes from x equals a to x equals b. So my integral is going to go from a to b. All right? So again, at this point, the physics is done. This is where the physics is done. All right? And so now the rest is math. So plug it into the calculator. Plug it into Wolfram Alpha, okay? Do whatever you need to do. All you need to know how to do is how to set this up. The math, that part is not as important as being able to set this up. okay? But for completeness, I am going to show how to do this integral. So this integral could be done with u substitution. So if I let u equals x squared plus y squared, and remember, y squared is basically a constant. So that means that du is 2x dx. Okay. So this is a u substitution, and so you can easily do that. Okay. So this integral will then transform into the integral of so here I have x dx, here I have x dx. So this is like minus k lambda times du over 2, and then I have over u to the 3/2. Okay. And that integral is fairly straightforward. What I like to do when I'm doing integrals is I like to just flat out guess. Okay. I just guess and check, right? So I know that this power is going to get raised by 1, right? So it's got to be something like x squared plus y squared to the negative 1/2. Okay. And then now I just got to get the factor correct. So I know that it's going to multiply. So when I take the derivative of this, it's going to multiply out a negative 1/2. And then when I do the chain rule, it's going to multiply out a 2. So if you just do the check, it's got to be that. All right. Take the derivative of that with respect to x, and you will get exactly this. All right. So the minus 1/2, when that comes out, that brings out this minus sign. And when I take the derivative of this, it brings out a factor of 2, which cancels out the 1/2. Okay? So that's how I like to do integrals. I just kind of be like, it's probably going to be this times something, and then I'll just take the derivative and figure out what that thing is. Okay? And then I'm evaluating that between B and A. So that means that my electric field, the x component of my electric field at point P, is going to be k lambda, and I'm plugging in b for x first, so I have b squared plus y squared to the 1/2, and then I subtract from that the same thing but with x equals a plugged in, so I have k times lambda over a squared plus y squared to the 1/2. So that is going to be my answer. All right. So I really encourage you to solve these problems purely in terms of variables because it's just more clear that way. So do that if you can. So we're going to do one more example, which is a semicircle of charge. I'm going to say a uniform semicircle of total charge Q. Okay, so here's our uniform semicircle. Okay, so this has a total charge Q, and we want to know what is the electric field at the origin. So the origin is right there. Okay, so we're trying to figure out what is the electric field right there at the center. And we will say that this has a radius r. Okay, so the first thing I'm going to notice here, so what we want to do is we want to figure out, just take, when you have a circle problem, circles, your integration variable will be an angle. Okay. All right. So yeah, just keep that in mind. So notice how here I had a line, so my integration was over x. But here I have a circle, so my integration variable is going to be over an angle. So I'm not going to have dq dx. No. I'm going to have dq d theta. All right? And so what is dq d theta? Well, I know that it's a uniform semicircle of total charge q. So the total amount of charge I have is q. All right? And the total amount of angle I have, if it's a semicircle, is pi radians. So this is dq d theta. All right? So I'm going to be using that because that means that dq is q over pi times d theta. Okay? So that's a, I'm going to be using that. Furthermore, so now let's look at just a random, so here is theta equals 0. Okay. And here is a random piece of charge. This is my dq. And it is located at some angle theta. Okay. One of the things I will notice is that this distance from dq to the origin is the radius of the circle. And that's a constant because it's a circle. It doesn't matter where you are in the circle. If you take another piece of charge right here, it's still a distance r, big R away. Okay? So my little r is going to be equal to big R, which is a constant. All right? So based on that, I can actually construct my dE. All right, so my dE is going to be, and this, I mean that when I put dE without an arrow, I mean the magnitude of dE. So that's k dq over little r squared. So I know that's going to be k times dq, which is q over pi times d theta, over r squared. Okay, so I'm just going to simplify that. K q over pi r squared times d theta. So this is my dE. All right. So now if I think about the electric field at Q, by symmetry, the electric field points down. Why is that? Well, if we think about this little piece of charge, it's going to create an electric field that points down that way. Okay? All right? Lost my train of thought here. Now, because of the symmetry of the problem, if I take this electric field or this charge distribution and I flip it this way, if I flip it, it's the same charge distribution. So the direction of the electric field has to point downward. If it pointed side to side at all, then when we flipped the charge distribution, we would also flip the direction of the electric field. Okay, so the total electric field, even though this little piece of charge creates an electric field that is not pointed up and down, by symmetry, the total electric field, once we add them all up, should point straight down. So my electric field at the origin is going to be minus J, and then all I should have to do is add up the Y components of these electric fields. Okay? So how do I get the Y component? Well, here's dE. All right? And so this would be the Y component of dE. These are alternate, or I can't remember what you call these when they're opposite each other. I don't know. But this angle is theta too. Who cares what the name is? Just understand the math. So I can see that DEY is adjacent to the angle. So this is going to be minus J times the integral of dE times cosine of theta, because that is, in this case, that is going to pick out the vertical component. So, you know, I should say this is a little opposite, but that's just because my coordinate system is rotated. Okay, so now I'm going to plug in for dE. I'm going to plug in for dE right here. Okay, so I have minus J times the integral of KQ over pi r squared d theta times cosine of theta. So I can see that my integration variable is theta. So that means anything that doesn't involve theta can be factored out. So I'm going to factor those out of the integral. So I have minus KQ over pi r squared j hat times the integral of d theta times cosine of theta. So now I have to do the limits of integration. So the limits of integration, it's over a semicircle. Here's theta equals 0. So this point right here would be theta equals minus pi over 2. Right? Because 90 degrees in radians is that way. This would be theta equals plus pi over 2. So my integral is going to go from negative pi over 2 to pi over 2. Integral of cosine is sine. Sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. So this integral is 1 minus negative 1. So this integral is 2. All right, that's the value of that integral. So my electric field at the origin is going to be minus 2 KQ over pi r squared J. Boom! All right, so we are going to also work on this stuff next week because I know it's tough to the uninitiated. So it does get a lot easier, though, trust me. So go ahead and I will see you in the